Okay, now what we'll see is, so let me go here. What we were studying was, oops. Okay, so what we were studying was a simple harmonic oscillator. So here was x equal to 0, and this system was oscillating back and forth. Okay. Now it turns out that if an object, so an object going in at constant velocity around a circle, it turns out if you take the projection of this motion along the equator, this projection will execute a simple harmonic motion just like that mass attached to the spring. So for instance, okay, well, let me show you that simulation. Okay, so let's go look at the simulation. Okay, so let's put this mass over there and we'll start it. Now this thing is rotating at constant angular velocity, and see, this light is projecting the shadow of this guy on this plane. And this guy, the motion of the shadow is exactly that of a mass attached to a spring. Okay, and you can use another lamp here and project another shadow here. So what we're saying is uniform circular motion is a combination of two simple harmonic motion. Okay. Now, if you guys remember the gravitation chapter, when we dug a hole through the earth, and if you fell into that tunnel, we said that the period of that motion, that was a simple harmonic motion, and the period of that was about 85 minutes. And so if you orbit close to the surface of the earth, your period would be about 85 minutes. So the motion of the space shuttle is a combination of two simple harmonic motion. Okay. So that's what this thing is showing. Yeah. Okay. And the next few slides go to the proof of that. So if that is the velocity, that v is the speed of the object, that's the velocity of the point. The x component of that velocity would be the velocity of the spring. And the velocity of the speed of this object would be a omega, and this component would be, here would be the angle you would measure. That angle would be omega theta, omega theta plus phi. And so the velocity of this would be just like the velocity of the mass attached to the spring. When it's, when this object is going at constant speed, it has a centripetal acceleration. The centripetal acceleration is given by that. If that's the centripetal acceleration, the x component of the centripetal acceleration, which is that, is exactly the same expression as that for a mass attached to a spring. Okay. All right, now so till now we were talking about frictionless systems, and unfortunately in the real world there's always friction present. So let's learn how to deal with friction. Okay. So let's look at a simulation. Let's show you a simple harmonic oscillator with friction. Okay. So right now this is frictionless. So friction is introduced by this damping constant. And see, this is a frictionless system and it'll oscillate forever. And now what we'll do is we'll put a little friction in and see what will happen. And now with the little friction, see that oscillation was dying down. See, the amplitude it was still oscillating, but the oscillation dies down. Okay. Now, there are systems where you want to kill oscillations. So for instance, the shock absorbers attached to your wheels. So every time you hit a pothole when you're driving, you don't want your wheel to be oscillating forever, because then the next 15 minutes of your drive would be bumpy. Okay, you want, every time you hit a pothole, you want to kill those oscillations real fast. So there'll be systems where you want to damp out the oscillations, and we'll be interested in that. Okay. All right, so let's look at how can you damp out an oscillation. Okay, so all right, so here's a way to model it. Okay, so this is the drag force, or the damping force, and we'll model that the damping force, the friction force, is proportional to the velocity. Okay, and the proportionality constant is the damping coefficient, and it's called B. So let's model this now. Okay. Okay, guys. I have to stop recording for a second.